Okay, so where we left off, I was just about to take a look at a metal inquiry. So let's just take the whole thing. I'm gonna copy it. Copy this, go back into the metals research, one response. All. Here is something that recently came to my inbox via one of the online materials exchange forums. Okay, so I just pasted that whole thing in there. Unfortunately, okay, on Tuesday we were looking at how to turn these into actual hyperlinks, and my copy paste did not work. I'm going to attach a file that will contain those hyperlinks because I think it's a little convoluted to do that inside here. Advanced editor. Maybe we can do it here. Yeah. No. Let's just start over. Just use that advanced editor. Let's see. Oh, there we go. So I just did a copy paste. When I'm in the advanced editor mode, the hyperlinks come through. Did you see what just happened there? When I did not have that. Well, there's no toggle switch to turn it off, but I turned on. If you're paying attention there, I turned on the used advanced editor, and that allows those hyperlinks to come through. Nice. Okay. So mail it, post it.
What is the mail now?
I don't know. I think it'll spam everyone in the class. We'll see. Just like, oh yeah, I'm taking recycling technology. Maybe I should do some work this week. Okay, so let's dissect this message a little bit. So this came from metalworld.com. So there are a number of online forums. This just happens to be one of them. Bailed UBC. And I will be honest, I do not know UBC. I don't know the I don't know what that acronym stands for. Let's take a look. Maybe it says in here. But it is aluminum scrap. Unbound. First of all, let's figure out what UBC means. Used beverage cans. There we go. Okay. So used beverage cans is going to give you a specific alloy of aluminum. And if you've taken your aluminum scrap out to the local recyclers, they typically don't want aluminum foil in there. They typically don't want a big chunk off your car. It's going to be a different alloy of beverage cans. So let's just do a little research here. Aluminum can alloy.
I think the lid's different than the container.
Yeah, all right.
The container's got some sort of a liner on the inside, and the lid has a different type of alloy. Although all cans plastic.
Yeah, we'll just kick around on Wikipedia here for a little bit. So, yeah, almost certainly this this little tab is going to be a different material. Sometimes Elementary schools will give prizes for bringing in those little can lids. You probably also know that the caps on the milk jugs are typically like a number 5 plastic, and they don't regrind as well with the jugs themselves, which are a number 2, a high-density polyethylene. So you're sort of doing the recycler a favor by doing a little bit of triage before it goes back into the stream.
So wouldn't it just be easier to make it all the same?
The question is whether it would be easier to make it all the same. And again, it goes right back to that same question of time, energy, and money. And I'm sure it's been tried, but if there's no incentive for the packager to make either a law that mandates that their packaging be recyclable, unless there's a law or it saves you money, why would you do it? So you might say, well, it's the right thing to do, but gosh, if it costs me more money and it makes my product less reliable as well, you're not going to do it. So yeah, it is. But I want to take a look at the actual the material. Okay, most metal beverage cans manufactured in the United States made of aluminum. We knew that. Some are steel, some are an aluminum alloy. The aluminum cans used in the U.S. and Canada, 92 to 90% aluminum, some manganese, some magnesium, some chromium, trace amounts of iron, silicon, et cetera, et cetera. So these things have an actual MSDS, so material safety data sheet, let you know that, you better not have any cadmium in there, you better not have any lead in there, et cetera. I've also found, and Shelley and I figured this, determined this, there's a little bit of plastic coating on the inside of the aluminum. If you let those things sit there long enough and you didn't have the plastic, the beverage itself, being acidic, is going to slowly eat away at the aluminum, and you're going to end up, with, drinking aluminum into your body. We talked a little bit about last time how trace aluminum has been linked to diseases like Alzheimer's. So there's that's the reason for having the MSDS, and I'm thinking that David DeFeer is going to discuss that a little bit on next week.
Well, what kind of plastic are they using? What grade?
Yeah.
Because you know that
Sure.
a lot of times we have big bottle cans in the car.
Mm-hmm.
Just like water bottles.
Mm-hmm.
Plastic is hot, toxins are released.
Yeah, it's a good question.
About that.
Yeah, let's take a look. I don't know what type of plastic.
It itself is untoxic. It's
I know.
Very toxic, very acidic.
I mean, that's why they have the plastic in there for, but most people don't even know that.
So it just says right here, plastic membrane. Yeah, I do not know storing waxy substance. So even back in the day, there was some kind of plastic or wax on the inside as just a very thin layer to keep the food materials from interacting with the metals.
Can we take one over to that machine and have it tell us? The machine you said you had over there that would tell you what's in?
Actually, I was just over in geosciences, and they're doing a elemental analysis for us on some biochar. I would think I think your time would be better spent emailing a beverage company and asking them what the plastic material is that they're using. And I think by law, they're required to disclose that information. Yeah?
Yeah, let me call Coca-Cola.
Well, I mean, we have a United States Department of Agriculture, and they're responsible for making sure that our health and safety is protected. So I know those things do get scrutiny.
Sort of.
Well,
Better than nothing.
plastic membrane, Okay, so there's a little bit of a message.
History of can.
Yeah. I want to take a look though at the alloy. And so it's mentioned there's a 3000 series and a 3150 series. Let's take a look at that. Let's just take a look for 34 or 3000. Let's find the MSDS on this. Oh, NIST might be a good one too. Okay, so here's your CAS number. Let's take a look at that, so we all know what that is too.
And how do you rerun those sheets?
So chemical abstract services, numeric identifier contain up to 10 digits divided by hyphens into 3 parts. The rightmost digit is an entire number. For example, 58-08-2 is a CAS registry number for caffeine. So every single element, compound, what have you, is going to have a CAS number associated with it, and you can see that aluminum metal, there it is, 7429-9-5. And affiliated with that is going to be just aluminum metal. And we looked at the dynamic periodic table. Misspelled table, that's all right. And so all of these numbers are more or less maps to and from other sets of information. So where is aluminum again? Number 13, I always forget how light aluminum is. So aluminum is the 13th element, just north of magnesium and south of silicon, or east of magnesium and west of silicon. If we go back to that CAS. So this number right there just means matter on planet Earth or in the entire universe with 13 protons in its nucleus. That's all it means. What's this number mean? Well, manganese, let's go back to the periodic table. Number 25, that's what that number means. Magnesium, 12 protons in its nucleus. So the next thing to consider is that this MSDS has a range. So if it's got less than 0.8% manganese, it is not a 3004-3104 aluminum type. It's just not. It has to fall in these ranges. Those 3 elements have to fall in those ranges. You can see that OSHA is listed. I do not know NTP or IARC, but I'm assuming those are easily findable as well. Another thing it mentions here, it says composition given are typical values, not specifications. So I may have just misspoken. It could be that you could go outside those specs and still be in these ranges. Okay. Occupational exposure limits. Magnesium oxide fume. You don't want any more than 10 milligrams per cubic meter of magnesium oxide fumes in your lungs for more than 8 hours. Manganese, you do not want any more than 5 milligrams per cubic meter in the air you're breathing for more than 8 hours. Aluminum metal, and I would, I would take some time on next week and ask David to go over some of these MSDSs. He's gonna know these things inside out much better than I do. But every one of these different, and let's actually look at ACGIH. ACGIH. Association of Advanced Occupational Yeah. They are defining the science, but I'm having trouble seeing if they've defined themselves. Occupational, maybe institutional health? I'm not sure. Let's take a look here.
I don't know what the ACG.
I'm not sure what the I is. Is that institutional health? Industrial hygiene. Oh, there you go. American Conference of Governmental and Industrial Hygienists. Okay. Last few years, rethink its purpose. Ongoing change in professional documents drives 2012. So, sounds like. Oh, 1938, okay. Core purpose, scientific journal. Yeah. So this happens. There's also like the NFPA, National Fire Protection Association, and it's more or less a group of volunteers, professionals saying, I'm going to put my time in, publish a document so that if people would like to know best practices, there it is. And they're only as powerful as their reputation. They're kind of there to help is what we're seeing. Okay, so there's OSHA, ACGIH, and they've got their own specs. Let's just see if there's any conflict. Well, it looks like magnesium oxide fume for the ACGIH is the same exposure limit as OSHA. I guess that's a good thing. And how these numbers are developed and arrived at, it typically involves some kind of lab animal. They've got a poor rat sitting there breathing the stuff, see if it gets cancer or whatever. And you can question that all you want, but it's the world we live in. We have a lot of toxins in the environment, and
We have a lot of rats.
we have a lot of rats.
Very cool.
And so what's mentioned here, metal machining, grinding operations may produce fine particulate dust. So that's why all of the heavy metals reclamation we've been doing, we've done in the fume hood. So you're not actually breathing the stuff. Heating, melting, welding, etc., brazing may also put this stuff in the air. Of course it does. Particulates may irritate the eyes. Solid, liquid, gas. Last week we looked at the periodic table. We sort of went through the virtual melting temperatures of all the metals, and at normal conditions, of course, these metals are solid. Says that there's no alkalinity or acidity. Here's the melting freezing range. So this tells you if you want to melt the stuff, this is how hot you've got to get it. And that's and typically as we were just reading in the metals forming for these cans, they're done in a cold deep drawing process. They're not hot formed. They're cold formed. Specific density. This means that this particular alloy of metal will sink because it's almost 3 times as dense as water. Not soluble in water. Boiling is going to be so high that we're not going to worry about that. Vapor pressure, that's the pressure at which it just turns into a gas at normal atmospheric pressure, so also not applicable. And so, if you find yourself working as a recycling technologist and working with these metals, it's in your best interest to know this data and protect yourself. If you find yourself in an unsafe working environment, pop out the MSDS, let your employer know, hey, I'm not allowed to be exposed to this according to OSHA, according to where these guys are, ACGIH. Wash hands, mild soap, et cetera, et cetera. Personal protective equipment, I know DeFeer is going to go over that. Ventilation. And so OSHA has other regulations and also ANSI has regulations in terms of, so this is the American, I always forget the ANSI. And these guys are the pros. American National Standards Institute. That's neat, they put a lot of their stuff right out here. Here's the, let's take a look at ASTM really quick. Oops. Formerly known as the American Society of Testing of Materials, so that's why it's always confusing. They've got their S and their T backwards, but so this society will be responsible for telling you what the density is, telling you what the strength is, telling you what the modulus is, telling you what all. This is where those numbers on the MSDS came from. Someone at a lab at NIST in Bethesda went through, cooked it, heated it, bend it, braised it, you name it, they put it through the ringer, and that's where this information is coming from. I also mentioned the NFPA a second ago, again, a national volunteer-based organization that writes these codes every year. I actually found an error in the NFPA when I was working at the Savannah River site in Savannah, Georgia several years ago. We were looking at how radioactive waste was being stored, and it was bizarre, but these things aren't perfect. There was a formula in there. Let me just kind of show you what I found. And again, it's the fire protection codes, and there was a code in there that was giving the probability of one building catching another building on fire, right? So, let's say you've got this building's burning over here. You've got some length right here. We'll just call that L1 of overlap. and you might have another length over here. This would be, let's just say the buildings might look something like this.
But I'll try to do that.
We'll call that, oops. We'll call this one L2. And so this is building 1, this is building 2. And the equation looks something like this. The probability of building 2 catching fire from building 1 equals, and there was a couple other things in there too. There was a D1, which is the distance between the buildings, and then a D2. And it was something to this effect. The equation I'm about to write is not exactly right, but you'll get the idea. It basically said that L1 over D1 plus L2 over D2. So in this case, obviously, the more overlap, the longer L1 is and the longer L2 is, the more overlap you have, the greater the probability of the things catching on fire. Now, it also said that the smaller D1 is, so the closer the buildings are together, and the smaller D2 is, the closer they are together on that side, the greater the probability of the one other building catching the other one fire. But what this equation failed to notice is that if you have two buildings like this, so here's B1 and here's B2, so they're actually touching, like their corners are touching. You have L1 equals L2 equals 0, because they do not overlap at all. Even though they're touching, D1 and D2 are 0, or as close to 0 as you like. So therefore, the probability of B2 catching fire equals 0. So these codes aren't perfect either. So when I was working at the Savannah Riverside in Savannah, Georgia, with plutonium, with tritium, et cetera, trying to figure out whether or not the fire department would be able to stretch their fire hoses from a little fire hydrant out to the building that was built 50 years ago, I discovered this flaw. And so, my point is, these things aren't perfect either. They're written by humans, and they get weird, they get complicated, and don't be afraid to be a whistleblower and speak up if there's an error. Is the message I'm driving home here.
Physically touching, you can't do.
Well,
It's going to be a very small number. But
you're right. So in fact, you're right. If they were touching and D1 and D2 were both 0, there would be an infinitely high possibility of them catching fire, right? I mean, you kind of have, 0 divided by 0. We can sort of argue that mathematically, but I think you get my point. The formula was overly simplistic and thus flawed. Well, we could also say D1, let's just do it this way, D1 equals D2 equals 1 millimeter. So it's finite, but nevertheless, the probability ends up being 0. Okay. So eye contact. So what they're saying is that.
Eat it, it's okay.
What's that?
You can eat it.
Well,
at the bottom it says ingestion.
it does say that. Yeah, if you end up with the stuff.
I think they mean on your normal use where you would drink from it.
Could be though. Yeah, it's.
Under anticipated conditions of.
Normal use of it. I think it's saying you can ingest from it and you won't get any hazards.
Maybe. Might also be saying you could actually eat a chunk of aluminum and it's go right through you, and it probably won't hurt you that much either.
You do it with the lithium.
Yeah.
lithium will actually balance out your mood.
I can't see it coming well off of there.
If you eat the correct amount of lithium, it'll actually balance out your mood.
Okay, this product contains trace amounts of lead and chromium. And so the point is, it is impossible to get every bit of, well, I shouldn't say impossible. It is extraordinarily cost prohibitive to get every amount of toxic element out of whatever material you're talking about. I don't know if you followed the Chernobyl disaster or not. There are pieces of Chernobyl in this room right now. I mean, when that thing blew, it was up in the stratosphere, it coated the planet, and there are chunks of Chernobyl literally everywhere on the planet right now. It's just kind of the way diffusion works. So, and in this case, it's in the manufacturer's best interest just to say there's going to be some lead and there's going to be some chromium that come along for the ride in this manufacturing process. There are processes to get rid of all of it, but no one wants to pay $100 for a can of Coke. Yeah, question.
How did we get to the place where we use so much toxins to store our food and make our things? How did we get to that where someone thought that it was okay to have this kind of hazard in our lives?
Okay, so that's a deep question. So how do we get to the point?
I looked at this and it's like,
How do we get to the place where there are toxins in our food?
where did we decide this was okay to make, store food or how did water, how did?
Well, okay, so for example, since we're looking at lead, and I can give you a perfect place to go. If you get a chance, this is a fantastic story because I think it'll answer your question. How did we get here? So it might take a little bit of looking around, but Neil deGrasse Tyson, Cosmos, lead. If you get a chance, I would take a look at this particular episode. I think I might have just found it. Okay, so it's a very ironic story, and I think it might help you understand how we decided it was okay. And the answer is, we didn't decide it was okay, we just found out it wasn't such a good idea. And again, and I'll be honest, I mean, every single one of these things is pick your poison. Now, what ended up happening, and I might not have all of the episodes exactly right, but there's this thing, back in the day in sort of early petroleum research. So if you know how old a rock is, a strata of the earth is, you will then have some sense of knowledge of how likely it is to find a petroleum product there, because there were certain times over the Earth's past where more carbonaceous materials were laid down because of what the Earth's biosphere looked like. So it was in the best interest of the petroleum companies to know how old the rocks were. Well, lead itself played an important role because there are different isotopes of lead that decay, thus telling you how old those rocks are. Very similar to carbon dating. It was just called lead dating, if you will. So the petroleum industry said, tell us how much lead is in that, and that way or a specific type of lead, we'll then know how old these rocks are, and we'll know how likely it is we're going to find oil there. Well, as the scientist was in his laboratory trying to determine, in very fine detail, again, very expensive research, but, well worth it because of the economic boon of getting access to fossil fuels. He needed to know, parts per million, parts per billion of lead isotopes in different rock samples. What he found, though, every time he walked into his clean room or his laboratory, he got a different result. He'd walk in on Monday and it'd be 10 parts per billion. He'd walk in on Tuesday, it'd be 20 or 30 parts per billion. Same exact sample, but different. And again, we're talking parts per billion. He's looking for tiny amounts of atoms in these relatively large samples. Well, what he found out, he was dragging the lead into the lab with him. It was everywhere. He's dragging it off the street. It depended whether he walked on a specific sidewalk or walked in the gutter or walked in the street or took off his shoes or wore a different pair of shoes to work, because it was everywhere, because it was in gasoline. And it was in gasoline because it made engines last longer. Lead is a fantastic metal. It's a lubricant. It's a lubricating metal that allowed engines to last longer, so it was economically, what's that?
It reduced knocking.
Yeah, it reduced the knocking. There were a lot of benefits to having it in gasoline. Then all of a sudden he goes, well, gosh, do we really want that much lead in the atmosphere? And as it turns out, well, no, you don't. It sticks to the little neurotransmitters in your brain and makes your brain not work so well. And that was discovered, right around the 70s. And so now he was at this crossroads where the very people that were funding him to do his research did not want to hear his results so you can see your question, how did we allow this to happen? There's no one answer. There's no one answer. It's the same thing of who killed the electric car? There's no one answer. You're going to run out of fingers in terms of pointing them in terms of how those things play out. So I can't tell you the answer. All I can tell you is that the way these things are discovered are somewhat circuitous. Okay, let's take a little break here, and then I'm going to get back in and show you a little bit of what I'd like you to do with your own metals inquiry for next week.